Okay, so last week we talked about object detection and we discussed how we can use like a very simple approach like sliding window or maybe template matching to perform object detection. And there were some issues like whether we can run those algorithms in real time or how efficient they will be. So today we are going to see like some more advanced version of the same sliding window approach, and we'll see like how that can be done more efficiently. And so what we're going to do is first we will talk about like how we can evaluate like any algorithm which is performing object detection. What's the metric for that? And then we'll look into this RCNN object detector. So this algorithm has like a series of methods. So we'll start with this basic one, which is called RCNN. This I think stands for region proposals and then convolution neural network. Okay. I think there was a question from Brad. The solutions for what will be released later this week. The solutions for programming assignment 1 and the midterm. All right. So last week we covered how we can use sliding window, and we saw that given an image, what we have to do is we have to just take a window which we will slide like over this image using some stride, and that window will have some kind of aspect ratio and some resolution. And using some stride, we will try to locate that window in all the possible locations in this image and extract features from those locations. And based on whether that location is like in the ground truth, which will tell you like whether there's a person present or not, that sample or that feature will be either your positive sample or your negative sample. And then you will treat those as your samples for training, and you can easily train a binary classifier, which can be maybe SVM, it could be a neural network or a simple linear classifier, which can distinguish between whether this particular patch or this particular block, it's a person or not. And during training, what you have to do is again slide like a window in the testing images, pass the extracted features from those locations to the trained classifier, and the classifier will tell you like whether there is a person present or not. And based on that, all the locations you can assign whether person is present or not, and that will give you like the results where you have positive samples. Okay, and then we also see that if you do that, then for each location you might get multiple detections. And the reason is, let's say we have a person here, and since we are sliding the window like with a very small stride, maybe 1 or 2 pixels, then all the nearby bounding boxes in this location will mostly be like positive samples. So, but in fact, we only want to predict one, and that's why we need some kind of post-processing. And then we covered how we can use NMS algorithm, non-maximal suppression, to get rid of multiple bounding boxes so that we have just one final result. Okay, so this was like the sample result, which we discussed last time, the final detections. Now, the question is how we can evaluate like a method, whether the method is performing well or not. We need some kind of metric for that. Okay, so visually you can analyze, that's perfectly fine, but you need to quantify that so that you can compare different algorithms. All right. So for example, in this case, you can easily say that the algorithm is performing reasonably okay, but still, it's missing some of the people here. For example, it's missing the person over here, it's missing this person, and there are a lot of other people on the background on this right, which this algorithm is not able to detect. And so these are called false negatives. And we also have like a detection over here. In fact, this is a tree, but the algorithm is saying this is a person. So again, these are like false detections. So we call these false positives. And so it means that the algorithm is not perfect. And it's not doing that bad, but it's not perfect. So then we need like some kind of metric which will say, let's say out of 100, the algorithm is, let's say, 80% correct or 70% correct, right? So let's see how we can do that. So before moving on to the metric, let's look into like how we can compute intersection over union. which is used to evaluate that metric. And this intersection over union, we also covered when we were looking into the post-processing and object detection, where we were trying to get rid of like over prediction, where we have too many bounding boxes for the same person, right? So it's the same formula. And let's say you have two bounding boxes, the purple one and the red one. So to compute intersection of union, what you do is you have a term in the numerator, a term in the denominator. So the numerator is this intersection. So how much of the area is overlapping between this bounding box and this bounding box? All right, so that's the yellow region here. And over union, the denominator is union. So union will say like, what is the total area which is covered by these two bounding boxes? And usually you use some kind of threshold. You also saw that in NMS. So there we were using a threshold of 0.5. And if the IOU is greater than 0.5, we say it's like a reasonable detection. But if the IOU is less than 0.5, we say it's not a good detection. All right, and the value of this IOU will be between 0 and 1. So 1 means like perfect overlap. So in that case, what you will have is the intersection will also be like the area of the bounding boxes. So that will be in the numerator. And again, the same area will be in the denominator because the union is also the same. So that will give you like the perfect score of 1. And the lowest score will be 0. That will happen when there is no overlap between these two bounding boxes. Right? So in that case, the numerator will be 0 because there is no intersection. And that will lead to a score of 0. Now, I think there are some interesting points here to note. So you might be wondering that what if, let's say the purple one is the ground truth, okay, the actual object location. And consider a detection where, let's say this red block is the predicted one. So consider a scenario where this red block is something like in the center. Okay, so it's much smaller than the purple one, but it's like almost inside this box. And in that case, so if you compute the intersection, that intersection will be the size of the smaller box, right? And in a way, you will say that it's completely over the box, so it seems like a good detection. But that's where like this denominator here, which is like the union, comes into picture. So when you will compute the intersection, sorry, the union, the denominator, then it will be the size of the bigger bounding box. And in that case, if you compute that number, it will be like way less than 1. So it means that the overlap is it plays some role, but it's not that important. So the important is like first of all, the shape of both the bounding boxes should be as close as possible, and then also the intersection should also be pretty high. Then you will get a high IOU score. So that's intersection over union, and let's see some sample examples here. And so this you can see that let's say the green one is the ground truth and red one is the predicted one. So in this case, like there is a very high overlap, and the shape is also like almost similar for both the boxes. And if you will compute score for these two, you will get something around 0.905, which is pretty high, close to 1. And in this case, you can see that there is some overlap, but there is some region which is not overlapping, so it's close to 0.5. And as you move the box away, you can see how your scores are going down. Okay, so in this case, you can see that there's a very high overlap. Still, like the threshold is pretty low, 0.39. So if you're using a threshold of, let's say, 0.5 to determine that whether this is a positive detection or a negative detection, so a prediction like this will be a negative one, even though you can see it's a very highly the predicted one is highly overlapping with the ground truth. All right. So if the score is 0.5, it means that there is a very high overlap. So it's not that it's somewhere in the middle. Okay, so and this is like 0 because there is no overlap between the ground truth and the predicted one. Now, there are a few terms I think which we should go through first. So the first thing is true positive, and true positive is given a ground truth, in this case yellow, and a prediction which is red in this case, right? So you will compute the intersection over union, and then you will also see whether the predicted class is correct or not. So in this case, the predicted class is also true bird, and if you compute the IOU, it's pretty high. It will be, let's say, 0.8. Then you will like prefix a threshold, let's say 0.5, and you will say that if the IOU is greater than 0.5, I will consider it as a positive detection, otherwise not. So in this case, the class is right, the IOU score is high, it means it's like a correct detection, and we call that true positive. All right. The second term is false positive, which means that you are saying that you have detected something, but in fact you are wrong. Okay, so let's see this example. In this case, there is a high overlap, right? But the predicted class is cat, but this is not a cat. So even though the detection was pretty good, it has a very high IUU score, but because like the class you predicted that was wrong, that will go into false positives. The other cases of false positive is you predicted like the correct class, you are saying it's a bird, but the intersection over union is pretty low. It's less than 0.5. And again, this detection will go into false positive. And the other false positive is when, irrespective of the class, there is no overlap at all. So that will also go into false positive. All right. So the important thing here is that it's not just like the overlap you have with the ground truth, the class is also important. And then the last category is false negative, which means that there was an object present, this is the ground truth, but you were not able to predict anything at all. So that will go into false negative. Okay, now keep this in mind and let's see how we can use all these terms to get the evaluation for object detection. Now, before we move on, I think there's one important point here. So let's say we have a person standing here and you predicted two bounding boxes. So there are two detections here. And let's say we have also done like all the post processing we need to do, like the NMS and everything, and we got rid of all the overlapping bounding boxes, but still we have these two detections left, and it could be that the threshold which we have set for NMS or the post processing, it was pretty high, and that's why we couldn't get rid of this bounding box orange or yellow. So depending upon which one has higher probability. All right, so we have two detections. Now, when you will compare with the ground truth, what you will have to do is you'll have to start with the bounding box which has high probability score. Okay, so for each detection, you will have some kind of probability score, the confidence which your network will predict. So you will start with the highest probability. Let's say that's yellow. Then you will match this with the ground truth. Let's say this comes out to be a true positive, right? Then what will happen is that ground truth, it's gone. I mean, you can't match that ground truth to any other predicted boxes. So in that case, even though this orange boundary box, it's the right class and it has a very high overlap with the ground truth, even in that case, it will go into false positive because you can match only one ground truth to like one predictions. There is no like multiple matching. All right, so now, given all those three terms, what we can do now is we can compute precision. And precision is like, it's determining like how accurate you are in your predictions. All right. And the idea is irrespective of how many objects were present, like in your testing image, let's say there were 1,000 objects present in the image, right? And you predicted only 100 objects. And out of 100, some of them will be right, some of them will be wrong. So right and wrong, it's like they will go into those three categories. Either they will be, two categories. Either they will be false positive or they will be false negative. Sorry, not false negative. They will be true positive or they will be false positive. Okay. So now precision is out of those 100 predictions, how many predictions are correct, right? That will give you the precision. It's like how accurate your detections are, irrespective of how many total ground truth bounding boxes you already had in your training, in your testing data, right? So it doesn't matter if you had 1,000 or you had 5,000 or 10,000 in the ground truth. You will not worry about that. It's just like the number you predicted and how many of them were right. So that's precision. And the way to compute that is it's simple. You take the number of true positives you have and you add like the true positives with the false positives. So this is like your total detections, all the bounding boxes which you have predicted. So that will give you precision. That's metric number one. The second metric is recall. And so now recall is something in which you have to take into account like how many actual ground truth bounding boxes you had in your testing data. So for example, if you had 1,000 bounding boxes, right, and you predicted 100, then your recall will be pretty bad because you're missing almost 900 bounding boxes which were there in the image, right? And let's say you had 5,000, then your recall will be even worse because you are predicting only 100 out of 5,000, right? You are almost missing your 4,900 bounding boxes. So it will be actually pretty bad. So recall takes into account that how many of the actual bounding boxes you are able to predict from your testing data. Okay, so the simple equation for this is again like the true positives you have, but at this time you don't count like the false positives in the denominator. The false negatives will come into picture. So this is true positives plus false negatives. And this is kind of giving you exactly the number of bounding boxes you have in your testing data. Okay, so total number of bounding boxes you have. So now these are the two terms, precision and recall. Now what you do is you will take your testing images, okay, and you will make prediction for all of those images. And so you will have a lot of detections, and each detection will have some kind of confidence score as well, right? So what you will do is you will take all those detections and sort those detections according to the confidence score. So this is showing like one sample. These are like different images in your testing data. And these are like just the IDs of the detections. So each image could have multiple detections, right? Multiple bounding boxes. And so these are just the IDs of the detections. And these are the confidence scores. So your network said like in this image, you had this kind of detection with the probability of 95%. And similarly like for the other detections. So what you do is you just sort these, all the detections, and then you compute like whether it's a true positive or a false positive, right? So what you can do is you can take that bounding box and compare with the ground truth, and if there is a high overlap with the ground truth and the class is also right, it will be a true positive. But if it's not a true positive, it's going to be a false positive, right? So in this case, let's say it was a true positive, and apart from computing these two values, what you do is you also accumulate these true positives and false positives as you go down this list. Right, so I will come to this later. First, let's talk about just the first row. Okay, so this image, this detection, it was chosen because it has the highest confidence score. And if there's a tie, don't worry about that, just pick any. So the same thing you have to do for your k nearest neighbor. There was a question, I think, from Furkan or someone. So don't worry about like which one to pick. So this one is a true positive. All right. So you accumulate that. So you have one true positive. You have zero false false positives until now. Now what you will do is you will compute precision and recall just for this detection. All right. So precision means how many true positives you have divided by how many total predictions you have. So the numerator will be 1, and denominator will also be 1, because you have only just one prediction when you're considering this row. So that will give you a precision of 1. All right. And if you compute the recall, so recall will be your true positive, and the denominator will be the total bounding boxes or the total objects you have in your testing data. So in this case, let's say we have 50 images. I'm not showing all in this table, so there will be more rows. So what you will do is your recall will be 1 over 15. Okay, so 50, I just assumed it's 50, but you can check this number. So depending on this, you will have that many objects in your testing data, right? So you will just compute that. That will give you your recall. Now you're done with the first row. It gave you some value of precision. It gave you some value of recall. Now you will go to the second row. Again, you will go to the image, you will check the detection, the confidence, then you will see like whether this is a true positive or a false positive. So in this case, it's a false positive. Now what you will do is you will accumulate this into these two variables. So far you have seen one true positive, and so far you have seen one false positive. Okay, so using these two, again, you will compute precision and recall. So your precision will be your number of true positives, which is 1, and total number of detections, which is 2. So 1 was the first row, and the second is the second row. So 1 over 2, that will give you 0.5. All right, and then you will compute your recall. Recall will be your true positives over total number of detections. So which hasn't changed, right? It will be the same recall value which you got here in the first row. So again, it's 0.06. I think there is a question from Vinay. Why confidence level is high, but false positive is 1 in second row? So your false positive and true positive has nothing to do with the confidence score. Now, your confidence score is just saying that how much confident you are that this detection is from this class, right? Or like the location of this detection is correct. So that's just the confidence score. So we don't use confidence score to compute true positive or false positive. We use confidence score just to sort this list. Right? You can see here that you have a decreasing order here. And that's all why we need the confidence score. The other way to use confidence score will be, let's say your network is saying, okay, in this image, we have a detection. This is the bounding box, and this is the class, but I'm confident, my confidence is like 0.3, right? So for that case, what you do is you have like another threshold to determine whether that's a detection or not. So you can, let's say, set 0.5. And then what you will do is all the detections which have a confidence score of 0.5, you will just ignore those. You will say it's not a detection. So that's like a pre-filtering. All right, so that's how you use confidence score. So don't confuse this with the computation of true positive and false positive. So again, there are like lots of thresholds, and I understand when it can be confusing. So let's actually go through that again. So we have mainly 3 kind of thresholds. All right, so the first threshold is which you can use on the confidence score. Okay, so for each bounding box, you will have some confidence score, and that straight away you can say all the detections which have confidence score of less than 0.5, you will ignore all those. All right, so that means in this table, when you will construct it, when you're sorting this, the final detection will have around 0.5. So after 0.5, you will not have any detection in this image. So that's threshold number 1. Then we have 2 other thresholds. All right. So another threshold was this intersection over union. All right. So this threshold is again just used to determine whether it's a true positive or a false positive or a false negative. So if the intersection over union is greater than 0.5 and the class is right, your detection will go into true positive. But if your intersection over union is less than 0.5, for example, this particular case, it will, even though the predicted class is correct, it will go into false positive, right? So that's the second threshold. The third threshold is like which you used for non-maximal suppression. And that was like filtering overlapping bounding boxes. So these three are different, okay? So let's, I hope that clarified your doubt. Okay, great. So, okay, now coming back to this. So what you are doing is for each row in this table, you are going to compute this precision and recall. All right, so we were on row number 2. So we computed precision, we computed recall. So let's go to row number 3. Now again, you have some detection and it's in some image. And also like keep this in mind, this is not like the same image. You are scanning like all the images you have in your testing data. All right, so you might be switching between images, but again, that's not relevant here. So in this case, we are looking into image 3. That's the detection. That's the confidence. Again, we don't need this confidence anymore. So this was just required like to sort this table, just ignore it. Now, based on like the predicted class for this bounding box and the intersection over union of this bounding box with the ground truth, you can determine whether this is a true positive or a false positive, the way we saw like in the last slide. And in this case, it's a true positive. So now you will look into like your accumulated true positives and false positives. So you have another true positive. One was over here. So you got 2, right? And you had one false positive from there. So now again, you will compute precision and recall. So the precision will be, you have 2 true positives and you have 3 total predictions. So it will be 2 over 3, that's 0.66. And to compute the recall, again, it will be, you have 2 true positives and the denominator will be like the total number of detections. So this turns out to be 0.13. And you will like repeat this step for like all the detections you have from your network. All right. Now, once you have this list, what you will have to do is you will have to plot these precision recall points in a graph. Something like this. Okay. So one important thing here, so like the intersection over union can have a range between 0 and 1, right? 0 means no overlap, it's pretty bad. 1 means perfect overlap, it's a very good detection. We have a range for precision and recall as well. So precision is like between 0 and 1. 1 means all the detections you have predicted, all of them are correct. Okay, so in this particular case, you predicted 1 and that was correct. So precision is 1, that's the maximum value of precision. And the lowest value of precision will be 0, which means that none of the detections you have predicted is correct. So that will give you a score of 0. So it's a range between 0 and 1. And same is the case with recall. So the maximum value is 1 and the minimum value is 0. So the score will be 1 when you have predicted all the ground truth detections using your network. You haven't missed anything. So that's a perfect score. Okay. And the poorest score will be 0 when you haven't predicted anything at all. So keep that in mind. A recall of 1 is good, a precision of 1 is good. A recall of 0 and a precision of 0 is pretty bad. Now let's come back to this curve. So what we do is we take all these values of precision and recall over here and we plot them into a chart here. So again, the y-axis is precision ranging from 0 to 1 and the x-axis is recall ranging from 0 to 1. So we will just plot all those points here and this will give you some kind of curve. And this curve is called precision recall curve. And this is something which you use for determining how good your object detection algorithm is. And you can compare different methods using this plot. So over here, you can see that at this location, it's saying that the precision was 1 and the recall was 0, right? Starting from here. And at this location, you have a precision of 0 and you have a recall of 1. All right, so based on the other points, you will draw this curve. And So I think let's have a quick question here. Okay, I think there is a question from Gentai. So let's go to that first. Could you please explain how to calculate recall? All right, so let's recap that. So I'm assuming that this is clear how you compute true positive, how you compute false positive, and how you compute false negative. Okay, great. So recall is simple. You take the true positives, right, the first column in that figure, and you divide with true positive plus false negative. So that's the formula you can easily use. But giving you an intuition, recall is how. So let's say you have a testing data, okay, and in that testing data you have, let's say, 600 images, and in those 600 images you have 1000 bounding boxes. Okay, so because one image can have multiple bounding boxes. So now in your ground truth, you have 1000 bounding boxes, and let's say you use some kind of algorithm to make the detection in all those images, and that algorithm gave you, let's say, 500 correct detections. Okay, 500 true positives. So your false negative will be again 500, right? So it means that out of 1000, you were only able to predict 500 bounding boxes correctly. So your recall will be 500 over 1000. So that's 0.5. Okay. And let's say your algorithm predicted 800 and you had 1000. So your recall will be 800 over 1000. That will be 0.8. So it's like how many of the bounding boxes from the ground truth you are able to detect perfectly. Okay, great. So I think you understood. And so let's go to the pop quiz. So the question is, so this is like the precision recall curve from that table which we just discussed. And let's say you got like two different curves, A and B, and you have like two different algorithms. So the question is like, which one of these is better? So I think most of you got it right. And A is a better curve. And let me explain you why. Some of you are saying that neither of them is better. And there is a comment from Sean, it depends on the application. There is another comment like A is better because it is more gradual and isn't learning too fast. Okay, so A is better than B. And the reason is at all locations, like you can see that you have a higher value of precision and recall, right? I think there is some background noise from, I don't know where. If you can mute your mic, that would be great. I think someone is trying to talk and there is a lot of noise. I think is it Sean? Yeah, we are not able to hear you. Probably it's just me, but it's just noise. Sorry about that. If you have like, if you're saying something, you can put that on chat and I will have a look. Okay. So if you consider any point in this curve, the red one, then the value of precision and the value of recall that will always be higher than the value of precision recall in this blue curve. Okay, and a higher value of precision and a higher value of recall is always good. So if you recall from machine learning, then you can compute F1 scores, right? And F1 score is like twice of your precision multiplied by recall over sum of those two numbers. And again, like if you have a high precision, high recall, then you get a high F1 score. That's another evaluation metric. So A is better. Now let's see like how we can get an exact number using this. So what we do is we just compute the area under this curve. And that area, we call that average precision. And that's the metric we use for evaluating any object detection method. Okay, so now these curves were pretty smooth, and in real world, you are not going to get curves like this, because if you look at this table carefully, these numbers will be like arbitrary numbers. They are not going to give you a smooth curve like this. So if you will try to plot those numbers in a real world, this is like something which you will get. Okay, so let's focus on like this plot on the left. Now, these are all the points from that graph, a point over here, then you have a point here, point here. So you can see that there's a lot of zigzag. So it's nothing like what we were seeing in the perfect curve in the previous slide. Now, what you do is you actually try to do some kind of smoothing in this curve, and there are different ways. And I think the first paper which tried to propose this kind of metric, they used like a 11-point interpolation. And we are not going to cover that because it's not used anymore, but let me give you just an intuition. So what they did is you will have values between 0 and 1 in this x-axis. And if you divide that perfectly from 0 to 0.1, 0.2, 0.3, 4, and until 1, so you will get like 11 different values. So then what you do is for those values, you will perform interpolation of these recall values. Right. So for example, if this is 0.1, you will look into what's the highest precision towards the right. So which is this value, it's like 0.66. So at this point, you will have a score of 0.6. Similarly, at 0.2, you will see like what's the highest value of precision towards the right, which is like 0.43 here. So you will get a value of 0.43 for 0.2. And then you will get like average values or interpolated values like that for all these points from 0 to 1. So you will have 11 such numbers. You just take average of those, and that will give you like the kind of an approximation of the area under this curve. And they call that average precision. But we don't do that anymore. What we do is we do interpolation like for all the locations in this curve. Okay, for example, here what we'll do is for this point, we will simply see like what's the highest precision. We'll just fill that region here, and then we'll come back. So whenever you have a dip in precision, you are going to check like what's the highest precision towards the right, and you will just use that value. So for this particular location, at this location, the precision is 0.5. But then you check that at a recall level of I think 0.13, you have a higher precision, right? It's like 0.66. So you just copy over or interpolate this value for all these locations. So you will get a curve like this. And then there is a drop because you will come here. And as you move to the right, again, the maximum precision value you have, which is 0.43 here. So you will just take that value and complete this curve. And you're going to ignore this curve here. Also a curve here. So now what this is doing, instead of doing this interpolation at fixed values like 0.1, 0.2, 0.3, that 11 point, you take like a more dense interpolation. Because right now it's showing only 1, 2, 3, 4, just 7 or 8 points. But in real world, you will have like lots of images in your testing data, right? And based on that, you will have lots of these points. So it's going to be a very dense plot. And then you will do like similar interpolation. So instead of 11-point interpolation, you will perform interpolation in all the locations. And that's what we do. And once that plot is finished, you will just compute the area under this curve. And these are like just these rectangles. You can easily compute like area of each rectangle and sum them up. And that will give you average precision. Okay, so it's called average precision because you are taking the average of the precision values at different recall thresholds, right? So this is like a recall of 0.1. So at recall of 0.1, you are getting a precision of, let's say, 0.66. So you are taking average of all these. So that's average precision. And a more, I think, used term is MAP, and it's used a lot. We call that mean average precision. So this is, again, you use the same curve, but you will have this kind of curve for all the classes, right? And you just average that number. That will give you MAP. Okay, so before, I think that was the evaluation. Before we proceed, any question on this evaluation? Okay, all right, so it's good. Now, so last lecture, we talked about how we can use a simple sliding window and maybe extract features from all those windows and maybe train a classifier to determine whether there is an object or not. But the issue was you had like a lot of locations to extract features from. And the other issue was you will get like a lot of background features because most of the locations you won't have any object, right? And the other issue was your feature extraction and then your classification. They were like two different steps. Okay, so it was not like an end-to-end learning. And I think there were many other issues. So these were like some of those. The other was like you had to do that at multiple scales, right? And then for multiple scales, you will extract features and then add to a training list. So that all of that is like too complicated, too time consuming. So what we will do is we will look into like how we can address all of those issues one at a time. And now we are going to look into like the standard CNN approach, which is used these days. Okay, so let's have a look at like the performance metric. And again, this is that MAP, mean average precision. This is computed on the test set of Pascal VOC. So this Pascal VOC, I think, was released in 2010 and, oh no, so 2007. So these are like the improvements. These are the improvements in MAP over time. So around this time, you can see like 2012, the performance is kind of saturated. It's not improving over years. But this is like when CNNs came into picture, and you can see like how this is going up. So currently, I think it's more than 90%, but around 2015, it reached this level 0.75. I think it was SST detector. And here we are starting with RCNN. I think then this is, I think, faster RCNN. So we'll cover these 2-3 variations. So this is like before CNN, it wasn't deep learning, just the classical approaches. Then these are like using CNNs. So for object detection, we have like many data sets out there. So this was Pascal VOC. Then there is ImageNet detection. It has 200 classes. Pascal VOC has only 20 classes. We have MS Coco as well. This is also used for segmentation. It has 80 classes. And in terms of number of samples, you can see that it's like roughly 500,000 images, which is a lot. MS Coco has around 120. So MS Coco is more for multi-label classification because there are multiple objects present in those images. So the last row you can see here for ImageNet, the average number of objects per image is just 1.1. So it seems like only some of the images have multiple objects. Pascal VOC it's 2.4, but MS Coco it's 7.2. Okay, so these are like the standard data sets which are used for object detection. Now, let's talk about like when we are doing object detection, what exactly we want to do. So we discussed last time, we need like the class prediction, which class that object belongs to, right? And we also need the bounding box for that. Okay, so if you think about that in terms of output, so for class prediction, you just need like one prediction whether that class is present or not, right? But for the bounding box, you can have different variations. The most simple one is like you can just predict like 4 coordinates, and those coordinates could be either your left top corner, XY coordinate for that, and then bottom right corner of that rectangle. So just 4 numbers can give you the bounding box. The other way is you can actually predict the center of the bounding box, XY, and then you can predict like the height and width of that bounding box. Okay. Then, so that's the main difference between classification and detection. So you just don't have. Okay, just give me a minute. I think the battery is dying for my earphone. So are you able to hear me all right?
Yes.
Yeah.
Okay, so this is just giving me warning. Just try. Okay. And is it fine?
Yes.
Okay, great. I just switched this and thankfully it worked. All right, so that's the big difference between classification and this object detection, right? So you have these additional parameters which you have to predict for the bounding box. Now, another nice way to detect like an object is what you can do is you can predict like at each pixel whether the object is present or not, and that's like more close to segmentation kind of approach. And we will look into that when we talk about image segmentation. Okay, so those were the differences we just discussed between classification and object detection. So now let's see like
Your audio is cutting out.
just take and I think mic is not working.
Professor, we couldn't hear you for the last minute or so.
So 5:30. Okay, let's do the old school. So are you able to hear me now?
I heard you that just then.
Okay, so where were we? So yeah, so let's see like how we can use a simple classification network to also perform object detection. And let's say we have this input image. We can take like any standard CNN. So these are different variants of the classifiers which we already know. So you have this convolution layer which gives you some kind of features in a form of feature map. Then you have some fully connected layers which will give you classification scores. You can apply softmax activation after that, and then you can make the predictions, right? So that will give you the prediction regarding just the class, whether this class is present or not. Now, what you can do is you can still keep that architecture, okay, make that classification head separate, right? And add one more classification head, which is going to predict like the bounding box for the object present in this image, right? So, and this for this bounding box, what you need is you need just the coordinates of the bounding box. It could be like the center and height and width. So it will be like for each object, you will just need 4 values, and you can perform a regression. So regression is like it will just predict some value, and you will compare that with the ground truth, and you can compute some standard loss for regression, which can be mean squared error as well, or it could be L1 loss as well. So now what you do is you don't touch this network, you don't update this, and you don't touch this one either. You just use the ground truth and train this head of the network. So this is some kind of partial training, right? So you will send the image as input. There will be feed forward. You just ignore this part, and there will be some predictions. So whatever it predicted, you will have some loss function. You just do backpropagation in this particular part of the network. So that way, what will happen is when this is trained, you can take your base network, right, and also attach this classification head. And when you pass in your testing image, so this classification head will determine whether the object is present or not, and this head will determine if the object is present, what are the bounding boxes. So you can, this is like a simple hack. You can use your existing CNN to perform object detection. All right, so let's see like what are the issues in this approach. So that's simple. You just train these layers. It could be L1 loss or L2 loss. And test time, you connect both. Okay, so now let's see there are what are the issues. First of all, the classification head will have C numbers prediction, because if there are C classes, for each class you will need some kind of prediction, right? Now let's look at the regression head. What you can do is either you can have class agnostic prediction, which means that this head doesn't care like which class is present in this image or not. It will just give you 4 numbers, and those 4 numbers will tell you whatever object is present in the image, this is the bounding box. Okay, so it could be a turtle, it could be a cat or rat or something. It will just give you bounding boxes. So that's called class agnostic. So for that, all you need is just 4 numbers from this head. The other variation could be you can have class specific prediction, right? So class specific means if you have C classes, for each class you will have 4 numbers, right? So it will be C times 4 numbers output from this particular head. And then the way to use that will be you feed in this the test image. This will predict the class which object is present, and then this will predict like bounding boxes for all the classes, right? Now what you will do is based on this prediction, only one of them will be active because it's coming out of softmax, right? Only one of them will be high. You will ignore all others and pick that class and consider the bounding box for that class from these predictions. Ignore all the others, and that will be your classification and then also the detection. So that's another way. Now let's say if you have 4 different classes in the same image, right? So you have a dog, you have a cat, you have 2 like instances of cat, and you also have a duck here, right? So then for that you need like 16 numbers from single image, right? So one issue you can clearly observe here that you have 2 instances, but your network was predicting only one set of coordinates, right? So if there are 2 instances, then that kind of approach will never work because your network doesn't know like which bounding boxes it's predicting. Either it's like this cat or it's this cat. So that's issue number 1. Now, let's say we only have 2 objects in this image, right? Dog and cat. So these are just 8 numbers. So now what's happening, depending upon like the number of objects or number of instances you have in your image, you are predicting different set of numbers. And that's not a trivial thing to do when you're training your network, because when you're training beforehand, you should know like how many numbers or how many predictions your network has to make. So that's a big issue. The other issue is if there are too many objects, then the number of predictions you'll have to make is also going to increase. So the variable sized output is one thing, then the increase in number of predictions is another issue. So then this is not like a realistic solution or a scalable solution. Now, so let's see what we can do to resolve this. And this is going back to like the sliding window which we saw in the last lecture. So what you do is you take your sliding window, put it in the image, and just say whether cat is present or not, dog is present or not. So then what you have to do is for each window, you have to make one prediction for each class. So then you resolve the issue of variable predictions, right? You only need to make one prediction per class for each bounding box. So in this particular case, you can say cat is not present, dog is not present. For this bounding box, you will say cat is present, dog is not present, and so on and so forth. Okay. So this is exactly what we did in sliding window. And that's why I told you like last time, sliding window, it's a very powerful idea. It has been used in like a lot of problems, very interesting solutions using this. And so this is like just another sample of that. Now, so these are some of the issues, like I think some of these we have already covered. So for sliding window, we already know we have to test like many positions and different scales. That issue still remains. And it's very demanding for CNN to like extract features from all these positions at different scales, right? So we'll have to do searching at different scales and have to search at different positions. So the solution to that could be, what if we don't look at like all the possible locations? What if we look into only those positions where we know an object might be present? Okay, so now if you remember, like we were doing key point prediction, right? And we also look into Harris corner detection. So if we use something like that, which tells us which region of the images are interesting, or which are the regions like where we can find potential objects. So that will reduce the number of positions and the number of scales drastically. And that's exactly what we do. So we only look at some subset of these positions, which we know that there might be some objects present. And using this idea, the RCNN was proposed. Okay, so we call these regions where there are potential objects, we call these region proposals. Okay, that's the R of that RCNN. And the goal here is like we will look into blobby regions, which like I think Harris corner detector also did. Okay, so there is high potential that if the region is blobby, there might be some object present. And we need like a class agnostic object detector, because we don't want to detect or determine these proposals based on the object categories. So we will detect these regions irrespective of what object is present, and that will be like a more generalized solution. All right. Now let's see how we do that. And of course, I mean, you can use your key point extraction or your Harris corner detector to detect these regions and use those as proposals. But that's not what like I think RCN paper did. So we'll discuss how they did it. So they used selective search. It was, I think, the paper which was recently released at that time in 2013. And the idea here was they start with like a very fine-grained segmentation of images, and we are going to cover this topic, I think, later in the course. But right now, just assume that we have an algorithm which can actually group these pixels based on their surrounding pixels, and you get like these smaller segments. And this is like a standard image segmentation technique which you can use. So once you have these regions, what you can do is you can consider each of these regions as a proposal, right? Based on the shape of it, location, you will get a proposal. Now, if you compare these proposals to like the proposals which you will get using sliding window, these are way less than that, because you're not covering like every location and every stride in this. And still, these are too many, but still, if you compare with that, it's far less than that. Now, that's the initial stage. You start with that. The next step is you try to group the nearby regions with each other and come up with like more coarse level segmentations. Right? And you keep doing that until you like club all the regions into just one bigger blob. That will be like your whole image. You keep doing that. And this way you are going to get like different sized or different scaled proposals. So you can see here that your proposals are mostly very small. and the proposals are increasing as you go further. And in this one, you have much bigger proposals, which are kind of representing like the full objects. All right. So then what you do is, instead of doing sliding window, you use all these proposals as potential locations for your objects. Okay, and then you use a standard CNN to extract features from these locations and classify. So I think we are almost out of time. So that was like the base idea which was used for faster RCNN, and the exact network details I think we'll cover in the next lecture. So any questions until this point? So can you hear me?
Yes.
Yeah, we can.
Yes,
Okay.
Professor.
Okay, great. I thought I was just talking and no one was listening, so that's fine. All right, so that's I think all I want to cover today. The rest of the RCNN and its variants we will cover in the next lecture. And if you have any questions, just let me know. And if not, then we can end it here. Thank you for attending.